Hello everyone, welcome to this 10th lecture on this course which is Introduction to Remote Sensing. In this particular lecture we will be discussing about image characteristics, how what basically image meaning, or especially I am talking about digital image from a computer point of view or data handling point of view. Also we will be discussing different types of resolutions. Though in previous lectures we have touched, but in detail we will see and how images will look different in different resolutions and of remote sensing images. As you know that a old saying is that a picture tells 10,000 words. We can add one more line in it, that a satellite image can tell 10,000 words. So instead of just 1,000 words, a satellite image can tell 10,000 words. The reason why we have added this line, because not only it is saying, but if you are having time series data, then it can tell you the changes which has occurred. So for change detection studies, satellite images are being used extensively because of availability of archive and other data sets. Basically what is an image, and that is basically a satellite image we are talking. Nowadays we use digital cameras, and even through our mobile cameras we take a picture. That is a snapshot, though it also makes a two-dimensional matrix, and you are having, depending on the resolution of your camera, you are having the size of pixels there. But it is a snapshot. There is a difference between a snapshot and a scanning devices, which we have also discussed in some other previous lectures. So satellite images are not really a snapshot except for geostationary satellites, but in this polar orbiting satellite these are the images scanned line by line, as like in your table or flatbed scanners it is done, that entire document or map is scanned line by line rather than a snapshot. So when we take a when you take a snapshot we call as a picture, but when we take a scanner and scan an image or part of the earth using satellite based sensors, then we call an image. So that is the one of the major differences between an image and a picture or a photograph. So photograph is just a snapshot, whereas it is a scanned line by line. So an image, by if we look the definition, an image is a pictorial representation of an object or a scene. Here we have to think that image is being taken by the sensor which are on board of different satellites. So this is line by line data acquisition is done. There are various forms of images. Earlier we know that there are analog images and digital images. So all satellite based remote sensing images are digital images. Originally they are acquired through those opto-electro devices, and they are all in digital numbers. Analog images like photographic, earlier we used to have photographic film, or we nowadays print also, so that we call as produced by photographic sensors on paper based media or transparent media. That was the analog, and various variations in scene characteristics are represented as variations in brightness or gray shades if it is black and white image. And objects reflecting more energy appear brighter on the image, and objects reflecting less energy appear darker. It is the same concept as in case of analog image, so in the digital as well. Digital image basically produced by electro-optical sensors. So these sensors, whether it is on a satellite or any other devices, they are all, so there is a lot of similarity between these tabletop or flatbed scanners and scanners which are in space. They scan line by line, they produce images of any document or map or part of the earth using this concept of electro-optical sensors. Now the unit of an image is a pixel, which is an abbreviation which is called picture element. If you recall in the previous lecture I mentioned that like in Landsat 1, the MSS sensor, it was not a perfect square, the pixel was not a perfect square, and there because it was one pixel was being overlapped with another, so we used to call as mixel. but nowadays that problem is no more exist in all our remote sensing sensors, so we call as a pixel. And so it is a unit of an image which is always square in shape, except in case of Landsat MSS. In future or in current satellites, this concept is going to remain, that unit of an image is pixel, and pixel is always square in shape, and these pixels are arranged as a two-dimensional matrix, and each pixel is associated with a number, and that number is basically the quantization number. So we will see that how but what basically they are recording is a value is, brightness value is being recorded. If an object is reflecting very high, then higher brightness value will be recorded. In terms of digital values, it will be higher value will be recorded. If it is reflecting very low, then a lower value will be recorded. If we see if we change these values, digital numbers, pixel values into the range of gray values, then the dark are showing the less reflecting value objects, and brighter are showing high reflecting objects, and because of the variation in the radiant energy at a discrete form, and an object reflecting more energy records a higher number of itself on the digital image, and vice versa. And digital image in our GIS terminology also, otherwise from mathematical domain also, that we call as a raster image. It is nothing but a two-dimensional matrix, and it is each unit, as I have already mentioned, of an digital image is called pixel. Pixel is always square in shape. However, overall size of an digital image can be either square or rectangular. So this is very important to note, that the unit of an image is a pixel, which is always in square, but overall size of an image can be either square or rectangle. No other than these two shapes an image can have. But when we go for when we want to show only a image of an arbitrary area or a circular area, then what would happen? So there is a concept which has been introduced, that no data. So the areas which are beyond this circle but within the rectangular or square are assigned a value which is no data value, and generally if we are displaying on the screen, then it is mixed with the same value as background value is given, and therefore we do not see anything there. So we feel that image is circular, but in fact in the computer the image can only have two shapes, either rectangular or square. However, unit of an image is always a square in shape. And when though there are images, if we zoom a small part of a digital image, and this is what we see, except these sharp the grid which you are seeing here. This grid is being just to use to demonstration, but in real zooming of an image you will not see these lines, these were the grid of the pixels, and because these are having some values. This is an example of 8-bit image. So we are having value 0 as well as 255. Total range of pixels values are available of total 256. So we in digital image processing or in our two-dimensional matrix concept, we call these are the columns and these are the rows, or also we call a scan line, or these call a pixel. And this is another very important thing to note, that origin of an image, a digital image, is always considered from the top left. This concept will be used later when we go for georeferencing, and there we have to change this one, because in georeferencing, that means when we bring the geographic coordinate systems to correct an image geometrically, then our coordinate system will start from bottom left corner instead of top left corner. So that thing will be, so therefore it is important to note here that the origin of an image will start from top left corner. Pixel values, as I have said, is the magnitude of the electromagnetic energy captured in a digital image, is represented by a positive numbers. Now this is very important, that an image, the value of a pixel will always be a positive integer value. I am going to repeat it again. It is very important that a value of a pixel of a digital image is always going to be a positive integer value. But in like in GIS or for other raster types, like for digital elevation models, there the cell value can be positive integer, negative integer, even a real value negative or positive. But in case of a digital image, the pixel value is always going to be the positive integer value. So this one has to remember, and they are basically in the binary digits or bits. So when we say this binary image, that means we are having a pixel value either within an image either 0 or 1. That means either black or white. No other shades of grey in between these two extreme shades, means black and white, can have. Then it is image is binary or single bit image. But when we increase this quantization or number of bits, then we get more number of values, or if we think in terms of shades of grey, then we can have more shades of grey between these extreme values, black and white. So that we will see little later. So each bit records an exponent of power of 2, that is, if it is 1 bit, that means 2 power 1 equal to 2. So either 0 or 1, total number 2. When we improves on this, the number available will improve very significantly. We will see that example as well. So the maximum number of brightness level available depending on the number of bits used in representing energy recorded. Of course, no satellite records at bit level. Of course, now there are either 7 bit, 8 bit, 9 bit, 10 bits, 11 bits, like NOAA AVHRR records data at 11 bits. So if but very standard one, especially because many of the digital image processing softwares are capable of handling 8 bits data, therefore 8 bits digital satellite images are the most common one, or they are rescaled so that they are it becomes much easier to use with the digital image processing software. So 8 bit satellite images are very popular. 8 bit means 2 power 8, that means the total number of values available for each pixel to choose is 256, and the values will vary between 0 to 255, total number would be 256 including 0, and 8 bit, as I mentioned, is the very common one. So just for completeness, if we see that 1 bit image, that 2 power 1 equal to 2, only 2 shades are available or 2 colors can be assigned, values are just between 0 and 1, total 2. If it is 6 bits, like in case of IRS 1C pen camera, we had 6 bits images, that means the total number of pixel values could vary between 0 to 63, total number were 64. In list 3 we had like 7 bit images, and that means the values were ranging between can range within an image depending on the ground conditions between 0 to 127 or total number 128. If it is 8 bit, as I have said, the most common one, then the values of pixels within an image can vary between 0 to 255, total 256, that means 2 power 8. 16 bit images with the satellite based remote sensing are not common yet, but definitely because things are improving, so the radiometric resolution is improving with future satellites. So hopefully we are going to have even the 16 bits, and you can see that the range is 0 to 65,535, total number 65,536, and here 20 bit images 2 power 24, that means 1.67 million number of pixels or values or ranges available for each pixel. And this 24 bit I want to emphasize here, because when we create a false color composite or color composite using 3 different bands of 8 bits each, then your output image becomes 24 bits. So that instead of having just 256 colors available for all 3, then it becomes 1.67 million colors. And see this the difference, what the difference it creates if we increase just 1 bit instead of 1 bit. If we go for 2 bit, see this is just binary image, black and white. So pixel values either are white just for representation, the one has been assigned 1, 1 has been assigned white, and 0 has been assigned black. So you are seeing either white or black pixels, no other in between. But if we go for 2 bit, then we are having black, we are having white, and in between as well. When we go for 4, again more number of values are increasing. When we go for 8, so the 0 value is assigned the black color, the 255 value has been assigned your white color, and rest of the values are in between. Total range is available here 256 to choose for each pixel. And as you, if you compare the 1 bit image and just see the quality of image, so as the bits have improved, that means the radiometric resolution has improved, and so the quality of image has improved. Your interpretation can become much more reliable. You can distinguish different objects much more easily as compared to in a binary image. So that is the advantage of having higher radiometric resolution images, which are becoming now possible. I was mentioning about the 24 bits images. So when you use the 8 bit data, 3 channels or 3 bands data, create a color composite, in this example a false color composite, assigning 3 different channels using this concept of additive color scheme and primary colors red, green, blue, then this image will become 24 bits image, and that means the each pixel can have values of the spectrum which is available is 1.67 million colors. So any value between those 0 to 1.67 million colors can come to represent. That is why generally colored images are much more useful as compared to black and white images of any channel or any band which we are seeing. That is why it is very useful, though in terms of quantization it has improved, but the basic thing limitation, if we wish to call, with each band will remain same. So this output image, because 3 channels have been combined, therefore instead of 8 now we are having 24 bits image. In case of this example about a particular sensor, that is IRS 1V list 2 image of Paonta Sahib of Himachal Pradesh area. So if we see the digital numbers, this is how it looks. Remember that these these boxes or grid which are just shown here for our own convenience, but image itself will never have. It is having just rows and columns, and in those you are having values in continuation. So this is how the values will vary between different channels, and once the values varies, when we assign the gray shades, then the image itself also varies. So from computer point of view or from digital image point of view, this is how the image is there, a two-dimensional matrix. Each cell is a pixel which is unit, pixel is a square, overall shape of an image can be square or rectangular. Now we come to different types of resolutions, and first we take the spatial resolution, which we have been mentioning a few times, which is basically if we look the definition, it is the ability to distinguish closed space object on an image. That means the resolving power. How nicely you can see the boundary between 2 adjacent objects available within 2 pixels, adjacent pixels. So if you are able to resolve that thing much easier, then we say higher spatial resolution images, and when we are unable to do that, then we call a coarser, relatively coarser. So this is a relative term. There is no highest spatial resolution images in terms of in the field of remote sensing, and neither there is a coarsest in that sense. So it is the ability to distinguish closed space objects on an image. Higher the value, for a pixel, that it covers a area because it is a square shape. So, if I say a 10 meter resolution image, I mean it is representing 10 meter of the ground in width and height wise or length wise. So, 10 square, that means 100 square meter of area is being represented by a 1 pixel of a satellite image when I say a 10 meter resolution image. But when I say 1 meter resolution image, that means I am representing now only 1 square kilometer of the area, width and height is 1 meter. So, a small area is now being represented. So, once you are having a very small value, in case of spatial resolution, we call as a higher spatial resolution. So, it is a inverse kind of relation. The larger the spatial resolution value of a spatial resolution, we say a fine resolution. Whereas, if we are having coarser, that we say larger the value, then we are saying is a coarser spatial resolution. When the value is small, like instead of 10 meter, when we are having 1 meter, then we say relatively a higher spatial resolution. So, one has to understand this, the spatial resolution is very important. As we are seeing, if we go through the history of present day remote sensing satellites, then what we find that a spatial resolution in Landsat MSS was available about 80 meter, now it has improved even to 30 centimeter in some panchromatic or multispectral data sets like in world view or global view and kind of satellites. Second type of resolution, which we will see further details of this, is a spectral resolution, that is the basically how many channels within available EM spectrum are there, what is the width of those channels. So, the location of the channels or bands, width, narrower the width, more number of channels, higher the spectral resolution. Broader the bands, means covering the large part of EM spectrum, and less number of bands are there within that part of EM spectrum, we say coarser spectral resolution. So, with the time this spectral resolution is also improving, and slowly we are going towards hyperspectral. There we will have spectral bands for each 0.1 micrometer as well. And this basically sensitivity of chosen lambda bands means at different wavelengths. That is another very important thing. The spectral resolution will also depend in which part of EM spectrum one is looking for, because that amount of sufficient amount of energy has to reach to the sensor to get recorded. So, that is another important thing. The third out of 4 types of resolution, the third one is the temporal resolution. And temporal resolution means the time between observations, how frequently a satellite is being revisited or is visiting the same part of the land again and again. If let me give you an example of NOAA AVHRR, means NOAA satellites. It is covering the same part of the earth at least twice in a day, in 24 hours. So, repeativity here is 2 times in a day, whereas a very high coarse resolution satellites might be revisiting that area again after 22 days. So, it is a 2 times in a day and once in a 22 days. So, this when this the length time gap or the time between observations becomes very small, we call a higher temporal resolution. So, on this front, NOAA provides higher temporal resolution, say as compared to our resource set or other IRS satellites or even Landsat. So, on that front, because the swath bit is much larger, being a coarser resolution, NOAA provides higher temporal resolution. So, it is a kind of trade off. And the last one among the resolutions is the radiometric resolution, that the precision of observations, it is not accuracy. Precision basically depends on the sensitivity of a sensor, whereas accuracy is in a statistical term. So, these are 2 different terms which are there, one has to remember. So, 4 resolutions: spatial resolution, spectral resolution, temporal resolution and radiometric resolution. These 4 types of resolution are known in remote sensing. We will see one by one details about these. In remote sensing, the resolution means resolving power, and the capability to identify the presence of two objects. How nicely we can resolve these two objects. Capability to identify the properties of two objects and how these properties of two objects are recorded in terms of different pixel values. If same pixel values are recorded for two adjacent objects, that means we cannot resolve, we cannot distinguish between these two objects, and therefore we will say poor, might be a poor spatial resolution. So an image that shows finer details is said to be a finer resolution compared to the image that shows the coarser details. And we will see the example here. Here what we are seeing, that is a 8 meter resolution. The pixels are looking very coarse and you cannot resolve anything here. Basically you cannot make what different objects are there. But if we see relatively, instead of 8 meter, if we go for 1 meter, now we can see different objects in a much easier. So the ability to resolve or distinguish between two adjacent objects is much better relatively in case of 1 meter spatial resolution satellite image compared to 8 meter. Another example instead of panchromatic, another example is given in the this false color composite, that this is 10 meter example. We are able to resolve things very easily, we are able to distinguish, but if we compare this image with 80 meter resolution, then things are not easily identifiable. So this is how the spatial resolution makes the difference. So higher spatial resolution means a smaller value here, a digital value, and more number of pixels will be there in an image, more number of rows and more number of columns would be there. But compare by here 8 times, in case of 1 meter, here you will have 8 times more number of rows and columns, but the quality will improve significantly. So size of smallest dimension on Earth's surface over which an independent measurement can be made by the sensor, that is what in sense the spatial resolution, and this is expressed by the size of pixel on the ground in meters controlled by the instantaneous field of view. So we will bring this one as well, this concept of instantaneous field of view or IOV. But basically when the satellite is looking completely downward, then we say the nadir IFOB, and when because if the swath is much larger, like in case of NOAA HRR, the swath is 2800 kilometer, then we will have nadir IFOB as well as we will have for an image oblique IFOB, and these the sizes of pixels are changing here. Whereas IFOB is a solid angle. So you say basically you can say is a 3-dimensional angle, whereas you are projecting on a 2D surface. So that also makes the difference. So the IFOB is a angular cone of visibility of a sensor, which is shown here. This cone is A, determines area seen from a given altitude at a given B. This is the area which is being covered. Area viewed is IFOB, and that is altitude this C, and depending on if it is very flying at very high height, then IFOB means the size of pixel, the coverage it will have much larger of the earth with the same sensor. So that is known as the ground resolution cell, GRC, or element or pixel. So it depends on as I mentioned that this is how the area is recorded an image, and this is the solid angle then is converted to this one. Now the second one is the spectral resolution. As said, that spectral resolution of a sensor refers to the number or location of spectral band sensors collected in and how wide those bands are. So initially when Landsat MSS was there, it covered a same part of EM spectrum, but it has the same width for at least for first 3 bands, and these were quite wide or broad. Later on, like in Landsat OLI series, that is Landsat 8, these bands are covering very small width of EM spectrum, focusing more on the where the threshold is available in the atmospheric windows for different objects. in part of EM spectrum. One, and number of bands have also improved. So, the location and number, that makes the spectral resolution. So, a good analogy may be how many crayons are in your coloring box. Do you have 8 or 64 colors? That makes the difference here. Here is the example. Now, in this one, MSS, TM, ETM plus and OLI. So far, whatever the Landsat series of satellites, all 4 types of sensors have been covered in this. In the background, the gray shades are showing the areas where we are having atmospheric windows. The white areas in the background are the opaque areas. But what we see here, the Landsat MSS, continuous data, one band was ending, another band was starting, without having much inputs from the threshold of these atmospheric windows, and that is why these were continued, sliced down in a small part, and later on in Landsat TM things improved, number of bands have increased and the width of band have reduced. So, if width is narrow, higher the spectral resolution; if width is large, poorer the spectral resolution; if number of bands are more, higher the spectral resolution; if less number of bands are there in sensor, poorer the spatial. If we compare Landsat MSS to the Landsat OLI, that is Landsat 8, see the difference. See now though the numbering has changed, but if we see say second here, Landsat MSS band 2 and this red continues, see it has become further narrower. So, it provides the better distinguishability of different objects which are present on the surface of the earth as compared to Landsat MSS data. And the other sensors are, other bands are also shown. You can see we compare Landsat TM, ETM, both were almost same, except we introduced one more band in ETM plus, which was the panchromatic band. Though this panchromatic band was made further narrowed in case of Landsat 8 OLI series, and all these bands 6 and 7 also made narrower, and instead of having one band ETM plus the 6th band which is thermal channel, instead of that thermal band which was a very broad, it has now having 2 band. So, if we want to say about the spectral resolution, in relative sense we would say that the Landsat 8 OLI series is having higher spectral resolution as compared to Landsat 1 MSS, because the number of bands have increased. Second, the width of these bands have also gone to very narrow in size. What we see that in black and white or in panchromatic, generally the bands are quite wider, but when we go for multispectral like RBB imagery, this colored image example is given, or a word view, then these bands are many more and narrower bands are there. So, we instead of like multispectral sensors, we instead of just having 1 or 2, now people are going for 15 channels, hyperspectral, and no discontinuity between one band to another. It is a completely continuous. Example is average sensor, and there are 256 bands and hundreds of channels, hundreds of bands providing near continuous reading of optical spectrum. So, entire part of EM spectrum between that range 0.4 micrometer to 2.5 micrometer is covered. So, any object which is present on the surface of the earth can be distinguished by these channels which are large in number. So, we do not have any gap left in this. Number of channels has increased, the thickness of these channels or the bandwidth has decreased very significantly, and that will ultimately providing higher spectral resolution. So, in this in case of spectral resolution, when number of bands increases, we say higher spectral resolution. When bands or channels becomes narrower, we again say higher spectral resolution. And now broadband is mainly common nowadays only in the panchromatic, but even in Landsat 8 OLI series this has further been reduced, because people realize that there is always advantage of having narrower bands rather than broadband. So basically if we are having broadband data, what is the advantage? Collecting radiation across broader range of lambda per band or the EM spectrum, so more photons and so more energy. That is because why this question can come, that why panchromatic channels are having relatively broader band as compared to multispectral channels. The reason basically is that in that part of EM spectrum, the energy which is required to be recorded by a sensor on board of a satellite is much more. So if you are having very narrow band, you might not have at that part of EM spectrum sufficient energy to be recorded by a satellite. So therefore, in early stages when our sensors capabilities were not up to as in that quality as today, we used to have broader band or channels. Now the electronics part is improving, so we are now going narrower channels, even 0.1 micrometer channels, and more number of channels are there. So broadband advantage is that it provides the sufficient energy so that it can be recorded by a sensor which is around 850 kilometer in space. Narrower bands whereas gives the more spectral detail but less energy, so the lower signal or lower signal to noise ratio. So that, as I have just mentioned, that if band is very less, there are chances that sufficient amount of energy may not reach, and this ratio is going to be much higher. So as electronics is improving, sensors are improving, and therefore it is becoming now possible to have more number of channels within the given EM part of a spectrum 1, and narrower channels are becoming possible, because we are improving on the sensors this SNR or signal to noise ratio. We are making further lower and lower, and therefore can increase the number of bands. More bands, also more information to store, transmit and process. This is a kind of trade-off. Everything more is not good in case of remote sensing, because then the application will change. Like for example of NOAA AVHR, it covers a large swath of the earth 2 times in a day, but at the same time it is having relatively coarser spatial resolution. So there is a trade-off, but the data storage requirement relatively is very less. But if I compare with say 65 centimeter spatial resolution data, then data requirement is very huge, and therefore processing time, transmission time, everything will increase exponentially or very highly significantly. So always it is not there. So because nowadays the choice is available. So we are having now different types of bands are available, different types of sensors are available. So first we have to decide for what we are going to apply remote sensing data, and accordingly choose that particular sensor which is most appropriate. For example, if you are going to cover a small part of a city at a very high resolution, no problem, the choice is there. You can go for 65 centimeter, even 30 centimeter resolution data, because your aim is to cover a very small part of a city. But if I am going to cover the entire India, say for example, then that high resolution remote sensing data is not going to be useful, because I will require too much of data to handle, to store and process. So I will approach and go for a relatively coarser spatial resolution data. So for every application, every type of data is not appropriate. Depending on the application, one should choose the appropriate type of data. For in case of a spatial resolution as well as for a spectral resolution and other temporal and radiometric resolution, which we will see. So if we continue on this, the broad and narrow band, but more bands enables discrimination of more spectral details, but to certain applications. If I am working for, say for example, for mineral exploration, I want to see the slight change in the any mineral concentration, say in case of copper, then I am looking those slight changes of the ground. So therefore, for me broadband channels or broadband data set is not going to be useful. I am looking for very narrow band data, more bands data. So immediately I should be able to pick that, okay, at this location I am getting the signals of the presence of copper on the surface of the earth. So there is a always trade off. Higher bands means higher storage requirements, transmission requirement, processing requirements. Higher spatial resolution, again storage, transmission and higher processing requirement. Lower spatial resolution, large area coverage but less thing, but you do not get those details. So depending on the application, one has to choose the data. Now the last in this one is the temporal resolution, that the time between observations, how repeatedly the data is the satellite is covering that area. Some satellites covers, like radar satellite generally will revisit the same area after 35 days, and whereas I have mentioned earlier also that like no IVHRR will cover in 2 times in a day. So relatively no IVHRR is having much higher temporal resolution as compared to other many satellites. The revisit time over the same area by a satellite we put as a temporal resolution. And the last one in this one is the radiometric resolution, that is the number of digital levels used to express the data collected by the sensor. So again, if we go for higher radiometric resolutions, we are going in higher in quantization, more data handling, more data storage requirements, but of course it is a trade off. So we are getting better higher quality images. So it depends on the application and the cost of project as well, because some projects may be very low cost project. You just require to prepare a land use map say at 10,000 scale. So you need not to go for a 65 centimeter or 30 centimeter resolution data. You may still prepare a 10,000 scale map for land use using say LIS3 data of 23.5 meter. So spatial resolution, radiometric resolution, all will depend that for what you are going to use the data set. As in case of radiometric resolution, higher you will go, more sets or more number of values to choose for each pixel are available. As you can see in 6 bit, 64, 7 bits, 128, 8, 256 very standard one, and then 24, 16.7 million colors. Now just to that is a repetition of this image, that 1 bit how is a binary image, how it looks there. Now if I compare just these resolutions between 2 sensors which were on 2 cartosets 1 and cartoset 1 and 2, the spatial resolution in cartoset 1 was 2.5 stereo. So it has a stereo capability, but relatively resolution was coarser as compared to length cartoset 2, whereas it is a 0.8 and mono, not stereo, monoscopic. Sensor type, of course both are panchromatic, collection time were different, swath, see the swath. As the spatial resolution has improved, the swath has reduced. Here the spatial resolution is relatively poor, swath is, and this fore and aft is because it is a stereo data collection. So when it is looking forward, it was collecting data at this the swath was 30 meter, when it is looking backward the swath was 25 kilometer. Revisit time here in cartoset it was improved, instead of 5 days in cartoset 1 it improved to 4 days, and orbits per day, of course these revisit times are interlinked, and altitude were also changed in this case. So this brings to end of this presentation. Thank you very much.